Welcome to a new session of control systems. In today's class 5, we are going to see the time response analysis. So, how to obtain the maximum overshoot, peak time, rise time, settling time for second order system when it is applied to step input. That is what we are going to derive. So, it's a derivation of time domain specifications. So, the standard form of second order closed loop transfer function of second order is given by C of S by R of S, which is shown by equation 1. So we know that for under-damped system, the zeta value lies between 0 and 1, and the characteristic equation is given by S1 and S2, where the omega n multiplied with under root of zeta square minus 1 is known as omega d, where omega n is the natural frequency and omega d is the damped frequency, whose value is given by equation 3. Now we have seen that for unit step input, R of t's value is 1. When you apply the Laplace value, the R of s value is 1 by s. Fine. When you take the response of output C of s, we are going to get the C of s, the formula, which is omega n square by s into s square plus 2 zeta omega ns plus omega n square. You simplify this equation with partial fractions, we are going to get the C of t value, which is nothing but equal to 1 minus e to the power of minus zeta omega n t by under root of 1 is zeta square sine omega d t plus theta. So this is a standard form of output of second order system when the input is unit step. Now with this underdamped system where we have C of t value, the waveform it is obtained to be in this fashion. You can see the oscillations are damped out and the steady state is reached in this expression as well as in this waveform. Now, how to study the time domain specification? So this is the damped out oscillations, and for the input step input, when we apply the x-axis and y-axis analysis, we are going to get the rise time, peak time, the maximum overshoot, and the settling time, which is shown by this graph. So this is the graph representation of second order underdamped system for unit step input. So these values can be derived as follows. So the rise time, it is defined as the time taken for a response to reach 0 to 100% for the very first time. So in generally for underdamped system it is ranging from 0 to 100%. For critically damped system it is ranging from 5% to 95%, and for overdamped system the same formula, that is rise time, is given for 10% to 90%. So anyhow we are interested for underdamped system which is from 0 to 100%. So it is defined as the time taken for the response to reach from 0 to 100% for the very first time. Now let the response reaches 100% of its desired value. So at t equal to rise time, so C of tr from the second order system output, we are going to make this C of tr equal to 1. Now when this is made equivalent to 1, we are left over with e to the power of minus zeta omega n tr by 1 minus zeta square sine omega d tr plus theta equal to 0. Now since the exponential term is not equal to 0, we can imply sine of omega dt plus theta equal to 0, or sine of omega d tr plus theta equal to sine n pi. For n equal to 1, this sine term will be changed to sine of pi, or it can be changed to sine 2 pi, 3 pi, and so on. Therefore, omega t tr plus theta is equal to pi. We are taking the for the value of n equal to 1. We are going to get the value of tr, that is equal to pi minus theta by omega n under root of 1 minus zeta square. Now this is a derivation of rise time for second order system when the input is unit step input. Now if at all you formulate the trigonometry for this analysis, we can replace cos theta by zeta and sin theta by 1 minus zeta square. So pertaining to this, the theta, when it is substitute, the value of rise time is given by pi minus tan inverse 1 minus zeta square under root by zeta whole divided by omega n under root of 1 minus zeta square. So this is the expression for rise time. On the similar analysis, let us go with the peak time calculation. So it is the time taken for the response to reach the peak value the very first time, or time taken for the response to reach the peak overshoot, that is maximum overshoot. So we'll take the standard output equation of second order system applied to step input, and we'll differentiate this C of t with respect to t, and we'll solve step by step and we'll equate it to 0. So you can see I have taken the derivation of dc of t by dt, and let us equate these values equate to 0, and with the sine term notations of cos term and tan theta term, we can get the value of uh, d c of tp by dt, which is equal to 0. And since this exponential term is not equal to 0, we are going to get the value of uh, tp, which is equal to pi by omega d, or you can replace this omega d by omega n under root of 1 minus zeta square. So this expression holds good for peak time. Then the peak overshoot value, it is defined as the ratio of the maximum value to the final value, where the maximum peak value is measured from the final value. So let us take C of infinity as the final value of C of t, and C of tp as the maximum value of C of t. Now according to the definition of peak overshoot, we are going to get C of t minus C infinity by C infinity into 100. Now we know that C of t is given by the standard second order output C of t value for unit step input. Now we will make use of this, and C of infinity changes to 1 minus, substitute the value of t as infinity, we are going to get 1 minus 0, which is nothing but value 1. For tp, we have substituted the value and we got the value of C of tp value as, just we have replaced the value of tp with the peak time value, and we have altered the equations and we have cancelled out the like terms, and we are left over with C of tp value, which is equal to 1 plus e to the power of minus zeta pi by under root of 1 minus zeta square whole divided by 1 minus zeta square multiplied by sine theta term. Now when you are going to take this value and cancelling out the like terms from this triangle, we are going to left out with C of tp value as 1 plus e to the power of minus zeta pi by under root of 1 minus zeta square. Now when you take the maximum overshoot formula and when you substitute the value of tp and C of infinity, we are going to get maximum overshoot value is equal to e to the power of minus zeta pi by under root of 1 minus zeta square multiplied the whole term with 100. So this stands as the expression for maximum overshoot. On the same basis, let us go with the settling time. So it is defined as the time taken by the response to reach and stay within a specified error. It is usually expressed as the percentage of the final value. In general, the tolerance error value is 2% or 5% of the final value. So from the standard output of second order system, when you take the 2% of tolerance and the sine term goes to the oscillations, that's why you're going to consider this term here. So when you take the value of t equal to ts, the value here for 2% becomes 0.02, and for the least value of zeta, this the numerator term will be equivalent to 0.02, and on taking the natural logarithm on both sides of this equation, we are going to get the value of ts, which is equal to 4 by zeta omega n. You need to remember that the time constant for second order system is given by t equal to 1 by zeta omega n. This makes the settling time equal to 4t for 2% tolerance band. What if I change it to 2% tolerance band to 5% tolerance band? Again, you apply the same natural logarithm values, and when you calculate, you're going to get the value of settling time is equal to 5t. So this is how the time domain specifications are derived for second order system, especially when your input is unit step input. So that's all for today's class. In next class, you're going to see the numericals based on time domain specifications. That's all for today's class. Uh, Share among the friends this particular video and subscribe to this channel and press the bell icon for the future notifications. Thank you.